Okay, I think we can let folks in and get started. Okay, people can hear me, right?
Yes.
Okay, cool. I see some response in the chat also. That's cool. I think we can let folks in. Okay. Okay, cool. I think let's get started. Perfect. I heard clearly somewhere. Okay, so now we are in lecture 9 of digital design and computer architecture. So hopefully people who are taking the class are having fun. We're going to raise the abstraction level today. So far, we've covered digital logic, starting from transistor as the abstraction level. And now today, we're finally going to move into architecture and microarchitecture. So hopefully it'll be fun. And we're going to cover a lot of interesting topics, but we'll start with the basics as usual. Okay, now that I can see my other Zoom also, that's good. So today we're going to cover von Neumann model and instruction set architectures, but I'm going to go through these slides as a reminder as usual. Remember that you have some extra credit potential with the lecture video and Moore's famous paper. So this is the plan for today and the next few lectures. I'm hoping to cover the green part today, the von Neumann model and LC3, an example of a von Neumann machine. But we're going to actually talk about MIPS architecture as well. So we're going to look at both LC3 and MIPS as examples of von Neumann architectures. LC3 is an educational computer that's developed by Pat and Patel in one of the books that you're reading. And MIPS is clearly a commercial architecture that has been successful in the past. And it's also successful in smaller embedded devices right now, like set-top boxes, TVs, etc. But it's a relatively clean architecture, although it has its own idiosyncrasies as well. So it's a good educational instruction set. In fact, it's very similar to RISC-V. If some of you have heard of RISC-V, I don't see that much difference between RISC-V and MIPS, frankly, except RISC-V is open source. And then we're going to talk about LC3 and MIPS assembly and programming. So we're going to cover some of that today also, but tomorrow we're going to go into assembly programming. So it'll be fun. You've probably seen programming constructs in some other classes, but you're going to see it at a lower level in this class. And we're going to do assembly programming and machine code programming as well. And next week, we're going to switch to introduction to microarchitecture and single cycle microarchitecture and multi-cycle microarchitecture. And then we're going to build up to out of order execution and other paradigms later on. Today, we're going to cover some microarchitecture as well, because it's very hard to cover instruction sets by themselves without going into implications on how an instruction gets executed in a computer. So today is really about an execution model, which is the von Neumann model, which encompasses the instruction set architecture of the machine as well as the microarchitecture. Okay, so hopefully that sounds good. This is quite exciting. So we're finally going to build a computer out of what we have learned so far. Okay, and these are some readings. You can take a look at them. So I'm especially going to follow Pat and Patel, chapters 4 and 5 today. But Harris and Harris has a very different treatment of similar material in its chapter 6. And you can see that you can also find the ISA and microarchitecture and instruction definitions in different appendices of the books. And then programming is going to be covered as well. And next week, you can see the microarchitecture readings. Again, these are all recommended readings. If you do them, I think you will learn a lot. And the books cover some things that I don't cover. I cover some things that the books don't cover. So there's some overlap between the things. But in the end, what you learn out of the lecture, if you learn the lecture perfectly, then that's great. Okay, so these are what I plan to cover today, basically. We're going to talk about the basic elements of a computer and the von Neumann model, and then jump into LC3, an example of the von Neumann machine. We're going to talk about instruction set architectures, LC3 and MIPS. We're going to look at different types of instructions, operate instructions, data movement instructions, and control instructions. We're going to examine their formats, and we're going to look at the addressing modes that they use to generate addresses so that they can bring data in, access data, for example. And as you can see on the right over here, we're going to cover the hardware-software interface, which is the instruction set architecture, which is a contract between the software and the hardware, what the software expects the hardware will provide. And we're going to also go into microarchitecture, as I mentioned. We're not going to delve into logic. We're going to assume logic. I'm going to show you some pictures of things that you have seen before in terms of the logic lectures that we have covered earlier, just to jog your memory, just to hopefully show that what we have seen earlier is building up to a machine today. Okay, so we're going to talk about building a computing system, and we will start with the von Neumann model. But before I define it, let me show you a picture that you have seen earlier, right? I showed you this picture in an earlier lecture, asking the question, what is a computer? Basically, a computer consists of three components: processing, memory, and I/O. And this is heavily influenced by the von Neumann model, as you will see in a little bit. And we will cover all three components in these lectures. And today is where we will actually go into this high-level picture of the computer and make it a little bit more detailed and construct it. Okay, so basically, we'll build up to a basic computing model. In the past lectures, we learned how to design combinational logic circuits, sequential logic circuits. And in the latest lecture, we learned how to analyze the circuits so that they can satisfy some timing requirements, if you remember timing, and also how to verify the circuits so that they can satisfy functional requirements as well as timing requirements. So timing and verification is extremely important for both combinational and sequential logic, clearly. But assuming that you do all of those well, now you're ready to actually build a computing system. And with these logic structures, we saw that you could build execution units. Remember the arithmetic logic unit, or the adder, for example. Remember, we could build decision units. Remember the multiplexer that can enable us to make decisions, right? We could build, for example, we also saw that you could build the priority logic, right? That gives you a grand signal based on the priority of different things that want that signal. Remember from the combinational logic lecture, and also I covered it recently as well. We could build storage units also. We could actually store data, store instructions, etc., as we will see, and then retrieve them later. And we could also build communication units. Even though we didn't explicitly talk about communication as much, all of the wires we design in our system is really about communication in the end. You could make it more sophisticated, turn it into networks, etc. We're not going to do that in this course. You will see it later in a computer architecture course if you take it, or a VLSI design course, for example. But communication is always there, right? You need to communicate one signal to some other from one place to another place, and that is communication. A wire is a communication unit, essentially. That's the simplest communication unit. So basically, we know how to build all of these at this point, and all are basic elements of a computer. Today, we will raise our abstraction level and combine these things. Essentially, we will cover the interface and the microarchitecture. Interface will be important because interface will expose to the software what we can do underneath, how we can use these underlying logic structures to basically make something happen, make something the software wants happen. That's why the interface is extremely important. And microarchitecture is a design that will enable the interface to make it happen using the logic structures. That's why we have these beautiful abstraction layers, as you can see. So basically, we're going to use the logic structures to construct the basic computer model. So let's go to the basic components of a computer. As you remember from the first lecture, we would like to solve problems, right? And problems are expressed in terms of tasks, algorithms, and then they will be written in languages. Essentially, we want a task to be done by a computer. If you want a task to be done by a computer, you need two things. Oh, I went backwards. Okay, you need a computer program to specify what the computer must do. And you need the computer itself, of course, to carry out the specified task, right? Now we're going to look at both. What is a program? Program at the lowest level is a set of instructions provided to the computer. Of course, you can have a higher level of abstraction where you essentially write at a higher level language. In the end, that gets translated to the instructions that we're going to see today. Those are higher level abstractions of instructions at the higher level. They get compiled later into the instructions that we will see. But program essentially a set of instructions. And each instruction specifies a well-defined piece of work for the computer to carry out. This is essentially the instruction at the hardware-software interface. And we will see many of these instructions today and tomorrow. So what is the instruction? A definition of the instruction is that it is the smallest piece of specified work in a program. And essentially that the computer can carry out, let's say. An instruction set is the set of all instructions that a computer is designed to be able to carry out. These are all possible instructions. So we're going to see the instruction sets more formally later on. Okay, now let's go into von Neumann model. In order to build a computer, we also need an execution model of processing computer programs. So, okay, you have the computer program. What do you do with it right now, right? Now you need to actually have a model that enables you to process computer programs. Now there are multiple models, as we will see later on. We're starting with the von Neumann model, which has been the most successful model over decades and decades. This was developed in 1940s by John von Neumann. In fact, in his seminal paper with colleagues in 1946, he proposed a fundamental model, and that's himself. And if you're really interested, you can actually read this paper, which is long, but it's nice and clean. The language is a little bit different from today, given that it's almost 80 years ago. You can appreciate that probably. But basically, this von Neumann model consists of 5 components to enable the processing of computer programs. Now, this what I'm going to describe to you is going to be a more refined version of the von Neumann model. It's not exactly what he proposed, but the principles are exactly the same, essentially. So we're going to have the memory components. Memory is needed to store the program and the data that's needed to execute the program. We're going to see the processing unit. That's the second component that's going to process the instructions and data. We'll have input and output units so that the computer can communicate with the outside world, right? And we will also have a control unit, which controls the order in which instructions are carried out. This is like the maestro of the orchestra, right? Conductor, essentially. So we will have all these 5 components of the von Neumann model, and we're going to examine them. So throughout this lecture, we will examine 2 examples of this von Neumann model, LC3, Little Computer 3, and MIPS stands for Microprocessor Without Interlocking Pipeline Stages. You don't need to know what that stands for. It's just an architecture, basically, instruction set architecture. So I will mention, before I go into detail in von Neumann models, this is one model of processing instructions, processing computer programs. There are other models. Later, we will see data flow model, for example, completely different. But von Neumann model has been extremely successful. All major instruction set architectures today are von Neumann architectures, like x86, for example, which is the dominant instruction set architecture today. MIPS clearly, ARM clearly, RISC-V. They're all following the von Neumann model because it's very intuitive and simple. But this doesn't mean that it's not necessarily the highest performance enabler, as we will see later on. So keep that in mind right now. This is what's dominant today, and it's a very good way of thinking about designing computers. It's very clean. It helps the programmers in many ways because of the properties, as we will see in a little bit. And the programmer can also clearly distinguish between these 5 different components if needed, right? Input, output, for example, we clearly distinguish between them. Processing unit, memory, we distinguish between them. As a programmer, we don't necessarily distinguish between control unit, but control unit is really essential for enabling the programmers to assume something from the hardware, which means that instructions need to be carried out in program order, and the control unit enables that carrying out of the instructions in the program order. Okay, so keep that in mind. We're going to look at other models later on. So this is the pictorial view of the von Neumann model. This is from your book, Pat and Patel. You can see the same picture over here. Now we're going to look at all of these components one by one, and then we're going to execute instructions on top of it. And again, both MIPS and LC3 have the same components, essentially. Okay, let's start with memory, because it's very important. And we've already built memories, right? If you remember, this is our memory array. This was the bigger memory array that we discussed, but you know exactly how a memory is built. This is 4 locations, as you can see. You have 4 addresses, meaning addressability is 4. And then each location has 3 bits, right? Sorry, address space is 4. And each location has 3 bits, meaning addressability is 3. Basically, by accessing one location, you get 3 bits. So this is a 3-bit addressable memory. Modern memories are not like that. Clearly, usually they're byte addressable, as we will see. Whenever you access a location, you get 1 byte, as we will see. And you normally have actually much, much larger locations, right? You have more than 2 to the 40 locations, for example, in modern memories, as you probably can buy on the market, for example. So this is the simple example of a memory, but you can scale up also. Okay, so what is the memory used for? It's used for storing the programs that we want to carry out, as we discussed earlier, and also data that's needed by the programs. Usually programs operate on data that's either input or it's provided with the program. So memory needs to store both of them. Memory contains bits, as we have seen in the previous picture, and bits are logically grouped into bytes Bytes is essentially 8 bits, as you know already. And words. Words could be 8, 16, or 32 bits, depending on the definition of the word. So word is described or defined by the instruction set architecture. It's a contract between software and hardware. Again, bytes is very cleanly defined, basically. A byte is always 8 bits, but a word can be, depending on the definition in the instruction set architecture, it can be 8 bits, 16 bits, 32 bits, 64 bits, etc. Okay, so address space, we've already defined it, but I'm going to define it again because it's also described in the ISA. It's the total number of uniquely identifiable locations in memory. And in LC3, for example, Little Computer 3, the address space is 2 to the 16. You have 16-bit addresses. Not a whole lot, right? In MIPS, the address space is 2 to 32, 32-bit addresses. In x86-64, which is a much more modern instruction set architecture, the address space is up to 2 to the 48 today, but over time it may change, of course. So you can have 48-bit addresses, okay? Now, addressability is how many bits are stored in each location, in each address, basically. So you can have a computer memory that's 8-bit addressable or byte addressable or word addressable. So we will see that MIPS is byte addressable, x86-64 is byte addressable, LC3 is word addressable, but there is a version, later version of LC3, it's called LC3B, for B for byte, that's byte addressable. So this is, again, depends on the how you define in your ISA what your addressability would be. So addressability gets exposed to the, so there are two types of addressability that I should clear out at this point. One is the addressability that gets exposed to the programmer. What is the minimum, what does the programmer see that each location is storing? And that is defined by the ISA. And then there's a physical addressability, lower level. At the lower level, underneath, the memory can actually have a different addressability. That's not what I'm talking about over here. Here, I'm talking about what gets exposed to the programmer. But at the lower level, when you build the hardware structure, for example, you may actually build a bit addressable memory, right? You may actually say, okay, I have 1 bit stored in each location, and somehow I get different bits from different memories to satisfy the programmer. So that because the programmer wants 1 byte, okay? So keep in mind that what gets exposed to the programmer as what memory looks like may be different underneath when the memory is physically actually built. As long as you expose to the programmer what they want and what you promise to satisfy, there's no problem. And this is a very fundamental principle between the hardware-software interface and underlying microarchitecture and the logic. You promise something in the hardware-software interface, memory is byte addressable, and you have to obey that promise, basically. Otherwise, programmers go crazy, right? They cannot write correct programs because they're going to assume that each memory location will have 1 byte. But underneath, you can do anything you want, as long as the programmer sees what they're supposed to see based on the contract that you signed in the hardware-software interface. So hopefully this makes sense. So we'll see more examples of this later on as this course progresses, but this is a good place to introduce it because people can easily confuse in terms of addressability, right? Is it the property of the ISA or is it the property of the physical hardware? And the answer is both, actually. And what you are concerned with depends on who you are. If you're writing programs, you don't care about the property of the physical hardware in most cases. But to actually make your program work, you don't care about that. You just care about the property of the ISA. ISA says this is byte addressable, and that's it. You assume that the hardware provides it. If it doesn't provide it, they're breaking the contract, which is not supposed to happen. And if you're the hardware designer, then you need to know both, right? Basically, you need to say, okay, for the programmer needs to see 8 bits in 1 memory location. I'm going to satisfy that. But underneath, for performance purposes, I may want to design the memory in a different way. For example, I may actually have a memory that can give me, let's say, 128 bytes at the same time. But I just pick the 1 byte that the programmer wants and give it to them. Makes sense, right? Underneath, I can do that. Nobody is telling me I cannot do that because I say, okay, this is the better. I get better performance by getting 128 bytes from my memory right away. And in each location, I store 128 bytes. But I pick only the 8 bits that the programmer wants using a multiplexer, right? You know the multiplexer. You get 128 bytes. You pick one of those bytes. That's 128 to 1 multiplexer. Okay, so hopefully this is clear. And we're going to see more and more of this difference between what gets exposed to the programmer and what doesn't get exposed to the programmer later on. Okay, so let's look at the simple example this is a representation of memory with 8 locations. I say representation because this is what gets exposed to the programmer, for example. But this, you could also build the memory this way, right? So you can see there's an address. There are 8 addresses, you can see, so 3-bit addresses. And each address stores a data value, okay? So each location contains 8 bits in this case, 1 byte. So in this case, it's byte addressable, as you can see. And address space is 8 because you have 8 addresses, or 3 address bits, which means you have 2 to the 3 addresses, right? If you look carefully, value 6 is stored in address 4. So this is address 4, 100 is 4, and value 6 is stored there. And value 4 is stored in address 6. So address 6 has value 4, okay? So hopefully this is obvious. And you could imagine, let me go back quickly to the memory that I showed you earlier, this one, right? You could imagine easily extending this memory to 8 bits over here instead of 3 bits. Now, if this one stores 3 bits per location, you can easily make it D0 to D7, right? That's not hard. And then you can easily increase the address space by 1 address bit and have 8 locations. And that would be exactly the underlying implementation of this byte addressable 8 location memory. Okay, now let me quickly maybe jog your memory, not memory, but push your thinking a little bit. How can we make this bit addressable? So if you want to make this bit addressable, you need to be able to address every single bit, right? So you have 8 bits over here. You don't want to get 8 bits. You really want to get 1 bit whenever you address something, meaning that you really need to have 3 more address bits, right? To specify each bit over here. So your address bits is essentially going to be 6. So you will have 64 locations, each location storing 1 bit. And that's a bit addressable memory now, right? Alternatively, you can have a byte addressable memory like this. And the programmer specifies which bit they want. So you can basically get these 8 bits out. Sorry about that. You can get these 8 bits out in the underlying hardware. And then the programmer provides 3 more bits saying which of these 8 bits they want if you have bit addressable ISA. Then basically, after you get these 8 bits out in hardware, you put 8 of those bits to a mux, and the multiplexer basically selects the bit that the programmer wants. For example, let's assume that this is 8 bits, right? Well, it's clear this is 8 bits. And the programmer wants bit 1. So bit 0 is this one, bit 1 is this one, bit 2 is this one, ... bit 7 is this one. Programmer wants the bit at address 100,001. So 100 contains, in terms of byte, contains all of these. So we get all of these in hardware, and then we basically select the bit that's corresponding to address 1, which is this one over here. So essentially, you need a multiplexer that selects from these 8s and chooses 1 bit that corresponds to the bit address. So that's one way of making this bit addressable, as you can see, and that's an important way, right? Okay. There's one question which I will quickly handle, I think. What's the difference between address space of 8 and address space of, say, 8 bit? Does the latter correspond to the bus size? So address space is really how many locations do you have in memory? So if you go back over here, address space is total number of uniquely identifiable locations. It doesn't say how many bits you have in each location, okay? So address space can be specified as 2 to the 16, for example. So if you that means 16-bit addresses. Okay. So if you look at the 16-bit over here, that is the size of your address, but your address space is 2 to the power of the size of your address. Okay. Hopefully that's clear. In this case, for example, address space is 8 locations, since this is byte addressable, and each address is 3 bits. So address space is 2 to the 3 locations. Okay, so hopefully this was interesting. You can make the memory bit addressable as well. So let's take a look at word addressable also. Each data word has a unique address in this case. In MIPS, for example, there's a unique address for each 32-bit data word. MIPS is actually byte addressable, so you will see that in a little bit. But you could also specify words in a MIPS ISA, and each word has a unique address, and each 32-bit data word has a unique address. LC3 is word addressable. That you have a unique address for each 16-bit data word. So the word size is really dependent on the ISA, as I mentioned earlier. So this is one example. This is the example for MIPS. If you look at MIPS memory, word 0 is 32 bits over here. This is hexadecimal format. Word 1 is 32 bits, word 2 is 32 bits, and word 3 is 32 bits. And you keep basically increasing from the bottom up, let's say. That's convention in this case. And you can see the word address, right? This is word address 0, word address 1, word address 2, word address 3. So if MIPS was word addressable, you would be using word addresses. You cannot get a byte. Right? You cannot basically specify the byte within a word because you don't have anything else in the address, right? Your addresses go from 0 to 1, and each of them specify one word. Okay, this is word addressable memory. Okay, byte addressable memory, on the other hand, each byte has a unique address. MIPS is actually byte addressable, as I mentioned. LC3B, updated version of LC3, is also byte addressable. So MIPS memory actually looks like this. This is a conceptual view, not the physical view necessarily. Right? Conceptually, MIPS memory looks like this. Basically, words are still 4 bytes. You can see 4 bytes over here. Another 4 byte, word 1. Another 4 byte, word 2. Another 4 byte, word 3. So you can actually see the different words. But each of them has a byte address. Okay. Now the addresses are different, right? If you go back to the previous picture, addresses are word addresses. 0, 1, 2, 3. These are words. I didn't change anything in the picture except the addresses. Now the addresses are byte addresses. So all zeros is the address of this word. 0004 is the address of this word 1. Because why? Because each word contains 4 bytes. Now we are incrementing the address by 4 to go to the next word. And address 8 is the address of this word. Address C is the address of this word. And you basically keep incrementing by 4 because each word has 4 bytes. Yes, 4 bytes. And the ISA is byte addressable. Okay, now there's a question over here, which is kind of interesting. How are these 4 bytes addressed? Basically, now we have 4 bytes in a word. One of them needs to be addressed all zeros. Another one should be 0000001. Another one should be 2. Another one should be 3. Which one is 0? Which one is 1? Which one is 2? Which one is 3? Now here we're at the mercy of convention again, right? And you may actually remember, if you read Jonathan Swift's Gulliver's Travels, little endians and big endians are talked about in the book. And little endians break their eggs on the little end of the egg, and big endians break their eggs on the big end of the egg. And there's no real reason why they would do it that way except for convention, right? And this is the pictorial representation. You have an egg, assume that it's asymmetric. You have a big end like this, and you have a little end like this. And big endian people like breaking their eggs on the big side, right? And little endian people were ordered to break their eggs on the little side, right? And that's how you change the convention, for example, by ordering people to do things if you're the king, right? Assuming that exists. Okay, so basically, it's a matter of convention. This really is, again, specified by the instruction set architecture. So let's do 2 examples over here. So this is the big endian example, which is not MIPS, not LC3B. Basically, big endian means that LSB, so you have basically 4 bytes in a 32-bit word in MIPS, right? You have one is the most significant byte, which is the most important byte. If you represent this 32-bit value as a number, that's essentially the most significant one. And another is the least significant byte, right? That's basically the lower order bits. So big endian essentially means that least significant byte is stored in the higher byte address. Hence, big endian. Based on where the least significant byte is stored, you call it big endian or little endian. Little endian, which is what MIPS is, means that least significant byte is stored in the lower byte address. Okay, and this is really what we're going to follow in our lectures, but you should really know the difference between big endian and little endian. It's just a matter of convention of which byte address the least significant byte of a word is stored. If it's at the lower or little address, then it's little endian. If it's at the higher or big address, it's big endian. Okay, so basically, does this really matter? Not really. It's a convention. Within a single ISA, you don't care about. You just need to know so that you can lay out your data correctly, right, in memory. If you have a number like 32-bit number, you want to make sure that the most significant part goes to the higher byte in a word when you actually put something in memory. If you don't do that, then you will get a wrong answer if you have a little endian machine, of course, right? I mean, this really matters. There's a qualified answer to this, basically. Of course, you need to know this. You need to obey the convention, basically, within a single machine. But if multiple machines communicate, for example, you have a big endian system and a little endian system, and they have to share or exchange data, now things matter, right? because the little endian system assumes one convention. It assumes that the least significant byte is in the lower address. Big endian system assumes something else. You need to convert the value such that it gets transposed and it gets stored in a big endian way if you're communicating from the little endian system to the big endian system, and vice versa, basically. You don't need to worry about that at this point, but if you ever design a network of computers that have different instruction set architectures, for example, you have to deal with this. And it's like a language, right? There's different languages put the subjects, object, different languages have different subject, object, verb orders, right? Sometimes you put the verb in the middle. Sometimes you put the verb at the end. Sometimes you put the verb in the beginning, right? And if you translate from one language to another language, well, you'd better obey the word, the order, because you may not otherwise get a grammatically correct translation, right? Okay, so we're done with the big endian, little endian. You will probably dwell on it a little bit, and when you write programs, you will see why you need to care about it. Now, let's talk about accessing memory. We're still talking about memory, issues related to memory. And we're going to introduce two registers, memory address register and memory data register. But before that, let's talk about how we access memory. Basically, there are two ways of accessing memory. Clearly, as we discussed before, we can read data from a memory location. It's also called a load data from a memory location. Or we can write data to a memory location or store data to a memory location. And we normally use two registers to access memory. Again, this is not a requirement, but it's usually used that way so that you can put the address in the memory address register and expect the data in the memory data register. So that's what I said, basically. You have a memory address register and a memory data register, essentially. And to read from memory, there are two steps, basically. First, we need to load the memory address register with the address we wish to read from. Basically, put the address into the memory address register, and then wait for the memory to access itself using the address, right? There might be another enable signal to enable memory. We're not going to talk about that over here. But once you put the address, the memory with its combinational and sequential logic, it basically accesses things internally because you have an address in the decoder, right? And the data comes out in the corresponding from the corresponding location to the address, and it gets placed in the MDR by the memory. Okay, so there we learned that logic. Actually, if you go back very, very quickly, it'll take some time, but this memory exactly does that, right? What I showed you earlier. Yeah, this one. Basically, you put the address, ignore the write enable for now. That's going to be the next thing. You put the address, the data gets out sometime later. Sometime later, subject to the delay of the circuit over here, right? That's essentially what we are going to do. Actually, let me do it. Basically, address will be stored in a memory address register over here, and the data will be stored in a memory data register. And address will be put in so that we can read from that address, and then data will appear in that register after the combinational delay passes, so that the memory can actually provide the data. Okay, so hopefully that makes sense. So basically, we're adding registers to the beginning of memory and to the end of memory, if you will, so that we can read the data. So somebody's asking, so the MAR is just a big decoder? No, MAR is just a register. Remember what a register is? We're going to see the register actually later on also. It's really, remember the D flip-flop? Basically, we have if the memory address is 16 bits, you have a 16-bit register, 16-bit D flip-flops, basically. And that feeds the decoder. That register latches the address, and that is connected to the decoder so that the decoder operates on a latched address for a clock cycle, as we will see later. So it's really the input to the decoder. Okay, I think I already said the reading part. Let's look at the writing part. It's essentially very similar, except we need to provide not just the address, but also the data. So address goes to the memory address register, and memory data register. We put the memory data we wish to write to that address into the memory data register. And we activate the write enable signal. I'm not going to go back to the memory I showed you earlier, but there was a write enable signal, if you remember. We activate the write enable signal, push it high, and that basically says, activates a circuitry such that the location that is specified by the memory address register gets the data in the memory data register and writes it into that location. And it takes some time. You need to wait until that time finishes, and then you can move on and load the memory with some other address, for example, to do some other operation, right? That's why timing matters, basically. Timing is important so that you know exactly when the data will appear in the memory data register. Assuming that a memory takes one cycle, let's say one clock cycle, you need to ensure that you wait enough combinational delay, as we discussed, plus the delay of the latches. If you remember the setup time and the hold time of the timing, you need to ensure you wait enough time so that after you put in the memory address, after the clock cycle, right, at the beginning of the clock cycle, from the beginning of the clock cycle, and after you assert the write enable, hopefully at the beginning of the clock cycle again, you wait enough time and the data appears at the end if you're doing a read. And for doing a write, essentially, you need to do the same thing. You need to wait enough time. And this is all dictated by the clock cycle that you decide to have in your processor, for example, as we will see also. So all of this should be able to happen within one clock cycle, assuming you have a one clock cycle access memory. We will later break that assumption. We will make memory multiple access cycles, multiple clock cycles, because it just takes too long to access large memories. But don't worry about that for now. So basically, every principle that we discussed earlier for combinational and sequential logic still applies over here. Okay, I'm done with memory for now. We're going to get back to it, of course. Now let's look at the second component of the von Neumann model, which is the processing unit. And you've seen parts of the processing units. You can see an ALU and temp over here, maybe wondering what they are. But processing unit essentially performs the actual computations. So we call these things computer, right? Computer does computation, and this is really what the computer is designed to build. The processing unit can consist of many functional units that can do computation, arithmetic, and logic. And we start with a simple arithmetic logic unit, which you have seen before, ALU. It can execute on computational logic operations. And these are specified by the ISA again. In LC3, for example, you have add, and not. These are the logic operations that, computation operations that you can do in the instructions. In LC3B, XOR was added, for example, instead of not. In MIPS, you can have many more. Add, subtract, multiply, and, nor, shift left logical, etc. Basically, different kind of shifts and rotate instructions that I'm not going to talk about right now, which you can look at. So ALU processes quantities that are referred to as words. These are the data quantities. This is, again, a word. This is very similar to the memory word that we have seen earlier. But this is really the processing width of a machine. So if people talk about a 64-bit machine, for example, it's really the word length of the ALU. So you can operate on entities that are 64 bits. In LC3, the word length is 16 bits. It can operate on entities that are 16 bits. In MIPS, it's 32 bits. Word length is 32 bits. In x86 64, for example, there's a reason why it's called 64. The word length is 64 bits, basically. It can operate on, for example, 2 data values that are 64 bits. Now, this doesn't mean that it cannot operate on smaller values. It can also operate on bytes, for example, 8 bits. But the maximum value is really the word length. Okay, so hopefully that's clear. So if someone says, oh, I have a 32-bit processor, now you know what it is. It's really, it really usually refers to the word length in the ALU, what your arithmetic operations operate on, the quantity of the width of the data that the arithmetic operations operate on. Okay, recall, we have actually seen ALUs, if you remember. So this is actually a copy-paste from the combinational logic lecture. And I'm not going to go through this in detail, but I'm just going to show you that this ALU is a unit that can perform 8 functions. You can encode the function as a control signal, 3-bit control signal over here, as you can see. And you can see the word length. Word length is n over here. So this is an ALU that can operate on a word length of n. And in MIPS, for example, n is 32. In LC3, as we will see, n is 16. But you can also make it operate on smaller word length as well, if you design your ALU reasonably, of course, right? Okay, you can see that different functions denote different things that should be performed by the ALU. So if the function that's input here is 0, 0, 0, it's supposed to do AND. If it's 0, 0, 1, it's supposed to do OR. So this way, actually, now if you actually have an instruction that says AND, you know that you should give a control signal that specifies the AND in the ALU, right? Hopefully that makes sense. Now, actually, you can imagine how if your instruction says, for example, add, it's an add instruction, you'd better make sure that the control signal in your ALU is 0, 1, 0. And you'd better make sure that the right operands or right inputs, right data values are supplied to the ALU from somewhere, as we will see, so that you operate on what the add instruction specifies, right? As we will see. Okay, so there's a question. Do we usually have multiple ALUs? Can perform multiple functions at once? Yes, basically in existing processors, you have many ALUs actually. It could be 8, in some cases more than 8, because you want to do multiple things at the same time. But we're going to assume we have one ALU for now. We're going to build up to those machines that are called superscalar machines, meaning things that can do more than one operation at a time. But existing machines are more complicated. You have more than one ALU, absolutely. Okay, so this is how the ALU looks internally, for example, as you have seen in the combination logic. So nothing I'm describing to you right now is things that we did not cover in the lower level. Okay, so what else do you need in the processing unit? You also need fast temporary storage, and this is important. So basically, you need to supply the ALU with inputs, A, B, for example. And then you have an output, and then you may actually use that output as an input for another operation, right? Because you have another instruction. So to be able to accelerate this, you want fast temporary storage. So it's almost always the case that a computer provides a small amount of storage very close to ALU in modern systems, okay? And the purpose is to store these temporary values and quickly access them later, especially if they're needed very soon. So for example, let me give you this calculation that I want to do in my computer. I'm going to translate to instructions if I want, but I don't want to do that right now. You can imagine that this could be translated to instructions, right? I have A plus B, I compute that times C, I compute that divided by D. Now, A plus B I don't really need. There's an intermediate result that's produced. I'm going to input that to the ALU and do the multiply with C, which means that I need that intermediate result and I can store it in a temporary storage. Why do I want to store it in a temporary storage close to the ALU? Because I don't want to store it in memory. I can actually take the result of A plus B and store it to memory, but it's too slow. As we will see later on, memory is just too slow compared to a temporary storage that's small. So we don't want to store it in memory and then retrieve it again for future use because it's just too slow to do that. And memory access is much slower than an addition, multiplication, or division, or a small temporary storage access. Same thing for the intermediate result of A plus B times C. Again, that's an intermediate result. I don't want to go to memory and store because I'm not going to need it later on, for example. But I need it to be able to compute that divided by D, right? Okay. So basically, I want some temporary storage close to the arithmetic logic unit, functional units. And that temporary storage is usually a set of registers. This is called a register file. So that's why we have the ALU and temporary storage called registers. So I'm going to introduce registers, which is a clearly very important concept. And this is an architectural concept of registers, register file, register sets. So memory is large, but slow. And to tolerate that latency, we don't want to go to memory whenever we do the computation. We have a result. We want to store that result in the registers in the processing unit. Well, that's what this temp stands for over here, so that we can ensure fast access to the values to be processed in the ALU. And typically, one register contains one word that is the same as word length. And we have a set of registers that are addressable by the programmer. So we have this part of the instruction set architecture, essentially. This is called a register set or register file. So these are a set of registers that can be manipulated by instructions. So for example, an add operation can specify, I want to add register 5 to register 6 and store the result in register 2. Okay. So you have this temporary storage that you use as opposed to the memory locations, right? And then you bring the data from the memory into the registers first, and then operate using instructions in the ALU. And then when you want to write the result back to memory, one result, whatever result that you compute, you basically store the result using some other instruction from the registers to memory. That's the idea. So for example, LC3 has 8 general purpose registers. It enables you to be able to store 8 values concurrently at the same time that you may be operating on. Originally, x86 had 8 general purpose registers also, but later people figured out that 8 is not enough. So they added more. So these are numbered normally. So R0 through R7, for example, you have a 3-bit register number to specify which register. So this is a very small piece of memory, basically. What I showed you earlier, the 8 address memory is essentially could be a register file, right? So you have a 3-bit register number, 3-bit address for the register file, basically. Okay, register size, the word length, which is 16 bits. Word length is what the ALU operates on, as we discussed. So MIPS, on the other end, has 32 general purpose registers because in real life, you actually operate on many values together, and 32 was found out to be a good number. And these are numbered as R0 through R31. So you have a 5-bit register number. This is also called a register ID, by the way. ID standing for identification number. It's really a register address, if you will. And register size and the word length in MIPS is 32 bits because MIPS is a 32-bit machine. Okay, so how are these registers built? We actually know exactly how they're built, right? We call, again, this is a copy paste from one of the earlier lectures, which is a sequential logic design lecture. Basically, remember, we use D latches to store more than 1 bit. So each of these D latches stores 1 bit. We put 4 of them together in parallel and have a single write enable signal for simultaneous writes. And we can do simultaneous reads clearly from that. This is a 4-bit register, right? Instead of 4 bits, we designed 16 bits in LC3 and 32 bits in MIPS. And basically, we denote the registers like this in the logic level, right? You have a 4-bit register here with a write enable signal. There could be other signals, of course, as we discussed earlier, but I'm not going to talk about those because those are below our level of abstraction right now. I'm just showing you these so that you have actually a connection to the prior lectures. This is how we're actually building up. Okay, you can a register actually better built using D flip-flops. Remember, a D flip-flop latches data at the rising edge of the clock or the falling edge, and it can keep the data for the entire clock cycle. And we want that actually in a real machine because we want to be able to operate on the data coming from a register for the entire clock cycle, as we will also see later on. But basically, you want D flip-flops, and D flip-flop based registers are essentially look the same. Basically, you don't need to know exactly how it's built underneath, if you will, at this point. We have multiple parallel D flip-flops, as you can see, and this is a 4-bit D flip-flop based registers. If you really need to know what's underneath, I showed you this picture in the sequential logic design lecture, and maybe some of you remember this one, right? Okay, so how are these registers get exposed to programmer? The registers around the ALU, basically you have a register file. So a MIPS register file looks like this. This is actually from an instruction set architecture manual, for example. They have some names that you can use in the assembly programming. You don't need to worry about these right now. It's a bit confusing. You don't need to memorize it. Actually, if you're doing a lot of MIPS programming, you will get to memorize it. But you have register numbers, as you can see, 0 through 31, 32 registers. And this is by convention, they may be used for different things, as you can see, right? Okay, so essentially, you have register numbers, and you can address them in an instruction and also in your assembly language. That's the key takeaway over here. Let me take a look at a quick question. How do companies handle their custom extras, e.g. ML accelerators? They extend an instruction set. So that's a good question that I don't want to tackle right now, but you could enhance your existing instruction set. You could basically say, I have a multiply and accumulate operation. I have a big matrix that I can operate on, for example. That's another possibility. I have a matrix multiplication operation. Or you could actually design a completely reconfigurable accelerator, right? And basically call a function to be executed in the hardware directly. So there are many different ways of actually doing this, which we don't have really time to get into, but that's a very good question, basically. You could certainly extend your instruction set, no question. And I'm going to talk about some instruction set extensions, like the multimedia extensions later on, not necessarily in today's lectures. I'm going to mention it once, I think. Okay, let's go through the one Neumann model, and after that, we will take a break. Input and output are simple, actually. We're not going to spend a lot of time on the input and output over here. Essentially, these are things that are necessary for you to be able to get information into and out of a computer, right? Many devices can be used for input and output. They're called peripheral devices because they're really peripheral to the processing that happens. So when you run a program, they're not really fundamental to the processing. Program may need input, of course, user input, for example, or program may need output. It's really for communication with peripheral devices. They're very important, no question about that, but they're called peripherals for this reason, basically. So there may be many input devices. You can see keyboards, an example, mouse, scanner, etc. Output device, and you can actually imagine even better input device going into the future, right? Maybe your eyes are input devices, right? Maybe your mouth is an input device, right? Directly. I mean, of course, your mouth not directly, but maybe it's attached to something that can receive signals from your mouth and eyes, etc. So these are really based on the imagination of the people going into the future as well. Output, again, could be maybe your brain is something close to your brain is an output device, right? Again, I don't know, but it could be monitor, printer, disk, etc. In LC3, your book considers keyboard and monitor. We're going to cover that very briefly, but we're not going to go into a lot of detail over here. If you take an embedded systems course, for example, you will deal a lot with peripherals because embedded systems is all about communication with the outside world. You can build a system that can basically compute your heart rate, for example. Very simple, yes, and these systems clearly exist right now, but You need to be able to communicate with the peripherals to be able to compute your heart rate. Okay, now let's go into the control unit, which is really the conductor of this orchestra. And that's the last piece of the von Neumann model, as you can see over here. So the control unit is like the conductor of an orchestra. Everything happens because control unit enables it to happen, essentially. It really conducts a step-by-step process of executing every instruction in a program. And each instruction also has a process of execution, as we will see. It keeps track of which instruction is being processed. And to be able to do so, it has an instruction register, which contains the instruction itself. This is the encoding of the instruction. This is the instruction I fetched from memory. I'm going to process it. After you fetch it, you latch it into the instruction register. And that instruction is available in the instruction register until the processing of it gets completed. It could take single cycle, multiple cycles, we will see. Okay. It also keeps track of which instructions to process next via a program counter or instruction pointer. This is really the address of the instruction to process or the next instruction to process, depending on when you look at it, basically. But essentially, you can think of it as the instruction of the next instruction to process. And you basically sequentially go through instructions unless there's an instruction that changes the flow of control, as we will see later on. So this is very important. Program counter, instruction pointer. Program counter is not a great name. Basically, it counts. Basically, program counter, you start from location 0 and you basically increment it. You keep incrementing it, etc. But I like the instruction pointer because it's really a pointer to the instruction that is going to be processed next. So there's one instruction that's being processed. That's an instruction register. And PC or IP points to the instruction that's going to be processed next. IP is a nice terminology, I think. Instruction pointer. Intel uses it. Everybody else uses program counter. I like IP better, actually, because it's really does justice to the word, because program counter, you're really not counting the programs, right? Okay, that brings me to the programmer visible architectural state in an instruction set architecture. Essentially, what we have discussed, what the instructions can operate on, are all programmer visible, right? So the memory, for example, is programmer visible. This is an array of storage locations indexed by an address. And this is, you have a programmer visible memory space. Registers are programmer visible. And these are given special names in the ISA, as we saw, general purpose versus special purpose. And program counter, memory address of the next or current instruction, depending on when you look at the program counter, as we will see also, is programmer visible. So instructions and programs essentially specify how to transform the values of this programmer visible state. So this is extremely important concept, basically. There are other registers in a machine. There are other memories in a machine, but they may not be programmer visible. What you care about as a programmer is what is visible to you. And when you actually write your program, that operates on the programmer visible state, essentially. And this is also called architectural state. And it's extremely important. This is what the instructions operate on. Okay, so that actually almost finishes the von Neumann model. We've covered all of these five components, essentially, and defined the programmer visible state also. But I would like to also mention two key properties of the von Neumann model. That's really important. And we're going to come back to it later on also, because all of the other models are going to break some of these properties, at least one of these properties, let's say. So von Neumann model is also called the stored program computer, meaning instructions are in memory. So whenever you want to get an instruction, you fetch the instruction from memory. Program is inside the memory. To be able to execute the program, the control unit goes through memory and gets the instruction and basically decodes the instruction, figures out what needs to be done to the instruction, and then sends it to the processing unit. Processing unit processes the instruction, updates the memory as needed, and then the control unit gets to the next instruction. So we're going to see that model later on. But this is exactly why it's called the stored program computer, because the program is stored in the memory. So there are two key properties. One is the stored program. But the second key property is also very, very important. In fact, maybe even more fundamental to the von Neumann model. It's sequential instruction processing. So let's take a look at the first one. Instructions in a stored program computer, instructions are stored in a linear memory array, and memory is unified between instructions and data, meaning that the interpretation of a stored value depends on the control signals, as we will see later on. Whenever you access memory, you may get an instruction, you may get some data value. It depends on what you're looking for and when you're accessing memory, as we will see in a little bit. If you're fetching an instruction, you interpret the data that you get from memory as an instruction. That's why the control unit is extremely important, because the control unit says, okay, it's time to fetch the instruction. It basically accesses memory. Memory just gives you a data value. It doesn't know what's an instruction or what's not an instruction, right? Memory basically gives you the value that you want from that location, program counter, let's say, which is the address in memory. And then the control unit says, okay, this is the instruction in program counter X. And I'm going to treat it as an instruction, the data value that I get from memory as an instruction. Later, it decodes the instruction. And then the processing unit figures out that, oh, okay, I need to access memory so that I can satisfy this instruction's operands, right? So that I can put it into a register, for example. And that access to memory is a data access, right? Because you're doing that access at a very different point in the instruction processing, right? You're not doing it when you fetch the instruction. You're doing it when you actually execute the instruction, for example, as we will see in a little bit. So basically, from the perspective of memory, it's all data. Some of them may be instructions, yes. Some of them are data, but the memory doesn't know that. It all depends on how you interpret the data that you get out of memory, and that it all depends on the control unit, the conductor of the orchestra, who knows exactly what it's doing at any given point in time. Okay. The second component is sequential instruction processing. This is also called sequential execution. And this is really the dominant paradigm of how computers are designed today, which is the von Neumann model. But it's really the key example of a key property of a von Neumann model. Essentially, this says that you process one instruction completely at a given time, meaning you fetch it, execute it, finish it. We'll see that in the instruction cycle in a little bit. And the program counter or instruction pointer identifies that instruction. And then after you finish it, you actually advance the program counter to the next instruction, right? Except for control transfer instructions, okay? So basically, you sequentially go through the program one by one. Program counter 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, ... And you execute, finish one instruction, and the next instruction starts after the previous instruction finishes, okay? So this is really important. Again, as we will see, we will build machines that will look like it initially, but then we were going to break this property internally so that we can get higher performance. But again, this is a property of the instruction set architecture. We're not going to expose what we do underneath to the programmer. Okay. Okay, so here, this is a very good time to take a break because now we're going to go into the instructions and the LC3, a von Neumann machine. So let's take a 10-minute break. Let's be back at 15:19. And then we're going to continue with the LC3 and MIPS. Okay, I think we can get started again. Okay, so now we built up to the von Neumann machine, and I'm going to go into LC3, which is an example of von Neumann machine. And then we're going to see examples from both LC3 and MIPS. But before we go into that, when I actually was preparing some of these slides, PowerPoint gave me this when I actually wrote a von Neumann machine. So I have no idea if this is a von Neumann machine or not, but it looks kind of cool, but kind of irrelevant also, as you can see. So this is, I'm not sure what this is, but it's something that comes out of the PowerPoint as a recommendation for what you get when you write a von Neumann machine. It's interesting. I guess it makes the presentations fancy, but not very interesting content. So you can certainly make PowerPoint presentations with a lot of fancy pictures, but not so interesting content. I think that proves that maybe. Okay, anyway, jokes aside, this is a high-level view of the von Neumann machine, LC3, essentially from the book. You can see that there are different parts of the von Neumann model delineated in color over here. And I'm going to go through this at a high level first. First of all, it's going to be important for you to understand how to read this sort of diagrams. These signals that have empty arrows over here are called control signals. So this is a control signal. This LDIR load signal is a control signal. This is a control signal, control signal, control signal. So everything that has a white arrow like this, memory enable or read or write, are control signals, for example. And we're going to need the control signals to control different combinational and sequential components of a machine. You can see the processor bus, that's the communication wire over there, right? So we're also going to need data signals that are marked as these dark arrows, as you can see, bold arrows. And there are many data signals, as you can see over here. This is a data signal, processor bus carries data signals, etc. And we also see the memory. Let's start with the memory side. So memory is green over here. You can see that it's 16-bit addressable. Memory address register is here. It inputs 16 bits, and it gets 16 bits as the address from the bus. And that address gets generated somehow and put into the bus, which is not shown here, but we will see later on. And the memory gives you the data into the memory data register, and then you can put it back into the bus and get it into the register file. So the machine itself needs to provide the data paths and the control paths so that you can actually take a data value, take an address produced by somewhere over here, put it onto the bus, place it into the MAR, and then interrogate memory with it using the right control signals to memory. And then the memory responds into the MDR. And then the machine needs to provide the right paths so that you can get the data value from the MDR gated onto the machine. You remember that there's a tri-state buffer over here, which I showed you as an example later on. And that gets gated onto the bus, and then you can put it anywhere you like, depending on how the control unit controls the machine, right? So that makes sense, hopefully. So I'm not going to go through everything right now, but the machine needs to have the path so that you can actually have all instructions executed, and you can interrogate memory, as we have seen over here. So we saw the memory address register. I already discussed this. We saw the memory data register. It can be connected to the register files, for example, so that you can get a data value from memory and put it into your register file, or you can get an instruction from your memory and put it into the instruction register over here. So you can see the control unit over here also, right? And there's a program counter, as you can see. So the control unit consists of program counter and instruction register. So input and output, as you can see, there's a keyboard data register, keyboard status register. We're not going to talk about them as much, but you can read your book, which talks about them in some detail. And then there's a monitor with data and status registers over there. Okay, now let's go into the processing units. This is where computation gets done. You can see the ALU has 2 inputs, 1 output. Word length is 16 bits, as you can see. And ALU function is determined by a finite state machine that decodes the instruction, as I said earlier, right? Based on the instruction, you determine what the function to be executed in the ALU is at any given point in time. And you can see that the ALU inputs are coming from, one input is coming from one source register from the register file. And the other input can come from that source, another source register from the register file, or it can come from somewhere else that's not shown over here, which is essentially an immediate value that's part of the instruction, as we will see later on. But you can see there are 8 general purpose registers. This is temporary storage in the processing unit. And we're going to see more of this processing unit later on when we talk about instructions in a little bit. And then there's a control unit, as we have seen earlier, but there's an instruction register, which gets its value from memory. As you know, basically, we store instructions in memory and we fetch them one by one into the instruction register using program counter as the address to load into the memory address register. So we have all the paths to enable that now in this machine. And instruction register stores a current instruction that's being processed, and that instruction needs to be decoded in this finite state machine. And finite state machine basically outputs a lot of control signals, as you can see, to orchestrate the execution of that instruction, processing of that instruction. That's why this is the conductor of the orchestra, right? All of these control signals enable the orchestration of everything else in the machine so that the machine can execute the instruction. And then there's a program counter, as we discussed. It points to the next instruction to fetch. And the finite state machine, I already mentioned, it generates the control signals. And there's a clock, which is very important because it's a sequential system. And that clock is input to all the registers in the system. As you can see, it's implicit in the old registers, actually. But it's also input to the finite state machine. And this ensures that the instruction, the signals that you have, control signals that you have, are decoded, and you have the signals available for you for the entire clock cycle, both the instruction, both the control signals as well as the data signals available for you for the entire clock cycle, so that you can do the processing as efficiently as possible in one clock cycle. And then you can move to another clock cycle, etc., etc. So clock, basically, it's a sequential system, as we discussed. It consists of sequential components plus combinational components. And we've seen actually essentially all components over here: registers, muxes. This is an adder, as you can see, +1, incrementer, etc. And we will see more in detail. Okay, there's the ALU operation, as I mentioned. It comes from as an output of this finite state machine that decodes the instruction, generates a control signal. So if it's an add operation, this ALUK signal will be asserted appropriately to signify, to enable an add operation in the ALU. If it's AND, then it will be signified appropriately, etc. Right? And then there's a gate ALU signal, as you can see, like gate MDR and some other gating signals, gate PC signals. Some of them are omitted over here. This basically enables a component to put its result onto the bus such that it can go somewhere else in the processing system. So, for example, I want to have the ALU result. I just finished an add. I orchestrated. Add ALU results need to go into, for example, the destination register. I need to enable this tri-state buffer and no other tri-state buffer that's driving the bus. Just this gate ALU. I need to set this gate ALU signal to 1. And that comes from the finite state machine, as you can see, because it's part of the instruction processing. And the result gets put onto the bus and gets delivered to a destination register, which is specified again by the instruction over here in some way, and a load register signal that enables a write enable signal. Okay. Okay, I mean, you don't need to understand everything right now, but this is what I showed you. These paths are essentially can essentially show you that you need to design these paths to enable the processing of instructions. And as I've already said, this is the processor bus. It is 16 bits wide in this case, and it goes basically over the entire processor, and it goes bidirectional, as you can see over here. So you can load the PC over here, and then the data can come from the register file, etc. We're going to talk about that later on, essentially. Okay, so that was a quick treatment of LC3, a von Neumann machine. And you can see the different von Neumann components of it over here. Now, let's talk a little bit more about how instructions are processed. Basically, stored program and sequential execution are critical to the von Neumann model. Instructions and data are stored in memory. Typically, the instruction length is the word length. Not necessarily, but typically. The processor fetches instructions from memory sequentially. It fetches one instruction at a time, decodes and executes the instruction, and continues with the next instruction, basically. That's the sequential execution. The address of the current instruction is stored in the program counter. So if you have word addressable memory, the processor increments the program counter by 1 to go to the next instruction, assuming that instruction is the same as a word length, right? Instruction length is the same as word length. And that's true for an LC3. Now, if you have byte addressable memory, and if the instruction length is a word length, which is 4 bytes in MIPS, then the processor needs to increment the program counter by word length, which is 4, right? Because your memory is in byte addresses, as we discussed earlier, but we want to get a word out of it. So we need to increment the byte addressable address by 4. So basically, initially in MIPS, the operating system typically sets the program counter to this value, which indicates the start of a program. And then you go to this value plus 4, this value, and then that plus 4, and then that plus 4, and then that plus 4, so that you keep fetching and executing consecutive instructions until you reach a control flow instruction, which we will talk about, that changes the flow of control. Okay, let's take a look at a high-level program stored in memory. Again, you don't need to understand the program now. We will get back to it. We'll build up to it, actually. But this is a sample MIPS program, for example. This is the MIPS assembly you will see when you actually do your labs. There are 4 instructions stored in consecutive words in memory. Each of them actually one word. I mean, it's not clear from the assembly because assembly is a higher level abstraction that for the machine code, as we will see. And you can see there are 4 instructions here: load word, add immediate, sub. You don't need to know exactly what they are, but you can see that they operate on registers, different kind of registers. They have destination registers, source registers. Some of them have immediates encoded in the instruction, like -12 value. And there's a way to compute the address for the load word. And load word actually provides a word from memory address computed in some way based on the specification of the instruction. So we will see these instructions in much more detail soon. But you can see the machine code that looks like this. Machine code is essentially 32-bit per instruction. And this is the encoding of each instruction. And this machine code gets interpreted by the decoder. So this is what gets fetched from the program counter into the instruction register for every single instruction. And then this is what gets interpreted, decoded. The instruction gets decoded, as we will see in a little bit. And these different instructions are encoded in different ways, as you can see. Their opcodes are different, their register identifiers are different, their address identifiers, immediates are different, etc. Okay? So these get stored sequentially in memory. By convention, we go from bottom to up in MIPS. So the first instruction gets stored at the bottom. The second instruction gets stored next. Next instruction gets stored next. Next instruction gets stored next. And you know that MIPS memory is byte addressable. So the first address is, as I said earlier, 400,000 in hex over here. And then the next instruction is at 400,004 in hex. Next instruction at 400,008 in hex, and then etc. And then you can keep going basically until you exhaust memory if you have a huge program, for example. And program counter initially points to that program, that location in memory, which means that program counter is set to this. That instruction gets fetched, decoded, executed, finished, completed, and then the program counter is used to fetch the next instruction. Okay, so that's basically the execution model. And then you keep going through the sequential instructions until you get to a control flow changing instruction. Okay, so essentially, as I said earlier, an instruction is the most basic unit of computer processing, right? Instructions, or you can think of instructions as the words in the language of a computer, right? At the very low level language. An instruction set architecture is the vocabulary of the computer. So the language of the computer can be written as the machine language. That's the lowest level of abstraction, basically. Computer readable representation, that's ones and zeros. These are essentially the instruction format, instruction encoding. Or it could be done in assembly language. This is the more human readable representation. So if I go back to the previous slide I showed you earlier, this is the machine code. This is the more human readable assembly. There's no difference between them. So you can translate the assembly to machine code, basically. There's a procedure that does it. It's called an assembler. It assembles these instructions into the machine code by going and figuring out what the instruction should be translated into in terms of zeros and ones, in terms of the instruction format. Okay, but assembly is easier. Of course, it's human readable. What is more easier is a higher level language, of course, right? Like Java, Python, C++, C, that gets translated into assembly, which we're not going to talk about at this point. So we will study now LC3 instructions and MIPS instructions. But before we go into that, we're going to talk about the instruction cycle a little bit, processing cycle, essentially. Okay, so an instruction is made up of 2 parts, as I said, opcode and operands. Opcode specifies what the instruction does. It's essentially the code of what the instruction is supposed to do. And operands specify who the instruction is to do that thing to. Basically, what are the operands? Which registers do I add, for example, if my opcode is add? Which registers do I multiply? Or which memory locations do I get if my opcode is something that requires a memory location, right? Operand is essentially the values that you work on, if you will, in other words, in more simple words. And both of these are specified in the instruction format. Instruction format is also called instruction encoding. They're the same thing, essentially. For example, an LC3 instruction consists of 16 bits. And you can specify that bits 15 through 0 in Verilog format, if you remember. Bits 15 through 12, which means the most significant 4 bits, specify the opcode of the instruction, which means that 4 bits are dedicated to the opcode. And there, as a result, there are 16 bits, 16 distinct opcodes in LC3, right? Okay. And bits 11 through 0, the remaining 12 bits, are used to figure out where the operands are. And this depends, how you figure out where the operands are depends on the opcode, basically. So this is also called an addressing mode, as we will see later on. This basically, you'd have different addressing modes to figure out where your operands are. They may be in a register. They may be inside the instruction encoding. They may be an immediate value that's part of the instruction encoding. They may be part of the memory location, in which case you need to generate an address for the memory location, and bits 11 through 0 specify how you should generate the address. And we will see different ways of generating the address of a memory location if your instruction requires a memory location. So you can imagine these bits are all about operands. There could be other bits, of course, in different ISAs, but for now, let's keep it simple. Okay, so this is one example encoding in an LC3 instruction. This is an add instruction. So you can see, first of all, there are 16 bits. And you can see we're using 16 bits. Top 4 bits, 15 through 12, are add. So the fact that there's 0001 specifies that it's an add. This is the opcode of the add instruction. And once you have that opcode, the remaining bits are interpreted as follows, basically. As you can see, this is the destination register. This is one source register, and this is another source register. Okay. And don't worry about exactly, essentially what this add instruction does, it adds R2 to R6. It adds a value, and it specifies to the computer to add the value stored in register 2 to the value stored in register 6 and put the result in register 6. That's why it's called an instruction. It instructs the computer to do that, essentially. And by decoding the bits over here, the computer finds that out. Essentially, by looking at bits 15 through 12, the decoder in the computer says, oh, this is an add. Now, how I interpret the remaining bits, I know. I basically know that after the add, this is the destination register. And then maybe I look at some other bits to determine what are the other registers, source registers, as we will see. But you can actually easily decode this instruction by just looking at the bits in logic structures, right? For example, this is a 4 to 16 decoder, right? Basically, you have 4 bits over here, and each bit can take 2 values, and you can have 16 instructions. And based on the value of those 4 bits, you know which instruction you have, right? Okay, so that's a decoder essentially. And the rest is also different types of decoders, let's say, as we will see later on. So this is very important. This is the encoding of an instruction. Let me talk about instruction types before we get into the processing. So there are 3 main types of instructions, as I think we've kind of discussed, but we've never nailed it down like this. One is operate instructions. These are instructions that execute in the ALU, right? Add, and, etc. The second is data movement instructions. These are instructions that read from or write to memory. That's it, basically. You move data from memory to registers or registers to memory, for example. Okay. And then there are control flow instructions which change the sequence of execution. So we're going to see all kinds of instructions, and we'll start with some example instructions. Let me give you the high level code for this addition, for example. An example operating instruction, a simple one, is addition, right? High level programming language, you can do something like this. Variable A gets assigned B plus C, right? Assembly, very similar. Instead of doing this assignment, you just said add with some convention. The destination is A, and then sources are B and C, as you can see. So add is really mnemonic to indicate the operation to perform in assembly. B and C are source operands, and A is the destination operand. So these are called operands, as you see over here. And this is the semantic specification of the instruction. A gets the value of B plus C, okay? Now, we map the variables to the registers. There's later a mapping of the variables to registers. So this is not exactly assembly, if you will. You need to specify the registers in assembly also. This is a higher level assembly, I should say, perhaps, if you will. But in assembly, you really need to map the variables into registers. So assume that you say, I have B in R1, C in R2, and A in R0 and LC3. This is the mapping that I get. And we're going to also look at the MIPS, which is going to be essentially very, very similar. Basically, the fundamentals are very, very similar in all ISAs. That's why I want to cover two things over here. There's nothing that's different between the ISAs. So LC3SM looks like this, basically. You add R1 to R2 and store it in R0 based on this mapping of variables to registers. Okay? So from assembly to machine code, this is what you get. This is really the assembly. You can think of this as a variable level assembly as opposed to register level assembly. Okay, so if you encode this instruction, you need to do something like this. Basically, you need to open up the manual for LC3 instruction set architecture, figure out, okay, this is my opcode for add, and this is how I should encode the destination register, source register, and where I should put them. And this is how I should encode the source register too. And these have to be zeros. Okay, that has to be specified in the instruction set architecture manual. So a machine code instruction encoding looks like this, basically, underneath. What I showed you earlier, very similar. The opcode, the top 4 bits are 001, 0001, because that's the opcode for the add. And then comes the destination register, R0. And then comes the source register, 001, R1. And then at the bottom, in the bits 0 through 2 comes source register 2. And these bits have to be 000 for this register to register add format. Okay, there are other formats potentially, as we will see later on. And in machine code, you can actually also write it like this, right? This is 16 bits in hexadecimal. Basically, it's 1042 if you chop it into 4 bits at a time, right? Okay, now basically we've essentially done a simple compilation, let's say. We basically translated, let me go this way, translated this high-level code into assembly first, a higher level assembly, variable level assembly, and then allocated registers to variables, and then translated the assembly to register level assembly, and then translated the assembly to machine code that consists of bit level encoding of the instruction by going through an instruction set architecture manual that tells us how this add should be encoded. Okay, and we will see in your readings, you will see that manual, and MIPS also has a manual also, right? Okay. So instruction format or encoding, I've already basically given you. The operate instruction format in LC3 looks like this. Basically, you have it depends on the different kinds of instructions. We have operate, control flow, and data movement, and within them, you may have different instruction format categories also. But in LC3, which is simple ISA, operate instructions look like this in general. You have the opcode, destination register, source register 1, source register 2 in these locations specified by the bits, and then these are set to zeros if you're doing register to register operate. Okay, so opcode specifies what the instruction does. This is being redundant, but I'm going to go through that. Add is, for example, 0001, and is 0101, just to give you another example. SR1 and SR2 are source registers. These are where the values are stored. Source register 1 stores the value, the first operand of the add. Source register 2 stores the second operand of the add. And destination register is going to store the result of the add. And semantics of the add is to take the value in source register 1, add it to the value in source register 2, store the result in destination register. If the opcode is 0101, the semantics simply changes to AND instead of add over here, right? Which makes sense again, right? You could also have OR, XOR, etc. And you could have many different types of operate instructions. And this is an example. This is an example, as you can see, that I showed you earlier, which is not different from what I showed you here, right? This is an example encoding of an add that basically takes source registers R2 and R6 and adds it source result in R6. Okay, now let's take a look at an example in MIPS, which is going to be essentially the same, except the encoding will be different and the assembly will look a little bit different, right? So this is MIPS assembly encoding of the same. So if you go back to this high-level code, A equals B plus C. That's the MIPS assembly encoding of A equals B plus C. If you actually assign S1 and S2 as the registers for B and C, and this for A, okay? And these are the field values. You don't need to worry too much about it. Basically, how you look this up, basically, you need to know the encoding of the instruction. You just find this in the instructions that I say manual. And MIPS is a little bit more complicated. It's not as nice as LC3. LC3 is designed for instruction, for example, education, for example. MIPS is real, but ISA. Well, LC3 is also real, right? You can actually build programs with it, but it's not used commercially, let's say. Let's put it that way. But you can see that add is encoded this way. Okay, basically, you have the opcode. You need to have the function. So because all operator instructions have an opcode of 0, and function is the part that distinguishes from between them. So this is a sub opcode, if you will. And then the MIPS operator instructions operate such that RS, the value in the register specified by the bits in RS, gets added to the value in the register specified in the bits in RT. And then the data gets stored in the register specified by the bits over here. So basically, in this case, you basically add register 17's contents to register 18's contents and store the result in register 16. Again, this is what the instruction set manual specifies. And this is the machine code instruction encoding in bits, as you can see. And it's 32 bits as opposed to 16 bits. And it's a little bit more complicated, as you can see. This is shift amount, which is supposed to be all zeros in this case because it's not a shift instruction. This makes sense only in a shift instruction, for example. So instruction encoding is general so that you can encode all possible instructions that's specified. That's why you need some parts of the encoding that you don't use in every instruction. And that's if you really want to see the hexadecimal code. Okay, so instruction format is R-type. Let's take a look at the R-type instruction format in MIPS. MIPS has different instruction formats, and R-type is one of them. R-type has 3 register operands, 2 source operands, 1 destination operand, as you can see. So RS and RT are source operands, RD is destination operand, and 0 is always the opcode for R-type. Okay, so 0 is the opcode, and RS and RT are the source registers. RD is destination register. Shamped is a shift amount for only shift operations. Ignore that for now. And funct is the operation in R-type instructions. So basically, this is an add, for example. We will see an example of funct soon. This could be an AND, for example. This could be an XOR, for example. They all have opcode 0, but function is what distinguishes between them. And this function gets input to the ALU almost directly in a MIPS machine, for example. So it's really part of the opcode, but designers decided to be this way. So basically, if your opcode is 0, then you have to look at funct to figure out what the instruction is supposed to do. If your opcode is something else, maybe funct has some other meaning. So it really depends on the format of the instruction, right? Okay, so we need to read operands from memory also. With operator instructions such as addition, we tell the computer to execute arithmetic or logic computations in the ALU, right? But we also need instructions to access the operands from memory and put them into the registers, or take a register and put the result of the value in the register to memory. So we want to load the operands from memory to registers, and we want to store them from registers to memory. So next, we will see how to read or load from memory. Writing or storing is performed in a very similar way, but we will talk about that later. Basically, storing is the opposite of loading. You can imagine store instructions doing very similar things to the load, except they're moving the data in the other way around, right? Not from memory to registers, but from registers to memory. Okay, so let's take a look at an example in word addressable memory. So this is load word. High-level code, let's assume that you're indexing an array. The base address of the array is A, a large A, and the thing you're indexing is at I, and the variable is going to be stored in the A variable over here. So you take array A and take the word in location I of array A and then store it into this little a variable. Okay, assembly looks like this. This is higher level assembly again. This is not register level assembly. So this is without the register allocation. So you load from address A plus I, address is computed some way, the memory location over there and the data value over there, and then place it into this variable. Okay, so load is the mnemonic to indicate the load word operation assembly. A is the base address of the array you're loading from. I is the offset, or in other words, immediate or literal. It's essentially a constant that's indexed into the base address. So it could be A plus I, for example, if you store words in this array, right? That could be the address of the element that you're trying to load. And the variable small a is the destination operand. So semantics of this instruction at the assembly or high-level code looks like take the word in memory location address A plus I, place it into variable small a. Okay. Now we're going to look at load word in LC3 and MIPS. So let's take a look at LC3 assembly. Now we're going to make I constant. Let's say that the index is 2. We want to read element 2 as opposed to element 0 as opposed to element 1 or 3, right? And this is word addressable. Again, we want to read the word into that variable. This is a high-level code. And this is the LC3 assembly, happens to be. This is one way of doing it. There may be other ways, but this is one way of doing it. This is a convenient way that uses a nice addressing mode, let's say. So basically what this is, load register. Essentially, what this load register says, semantics is, take the, calculate the address of the memory location that we're going to load as base register, value in the base register, which is R0, add 2 to it, calculate the address, and then get the data value in that address, place it into register 3, which is exactly what we want over here. So in MIPS assembly, this is going to be a little bit different. High-level code may look like this. In MIPS assembly, it looks like this, basically. It's very similar in a sense. Basically, take the value from the base register stored in memory, stored in S0 register, add 2 to it, and then place it, place the data value you get from memory into register S3 here. Remember, this is word addressable. In this case, we're loading words and everything is fine. Soon we're going to see bytes. So these instructions use a particular addressing mode. So this addressing mode, which is how do you calculate the address of the operand, is called base plus offset. And the reason is you have a base register, you add an offset to it. That's the base plus offset addressing. And we will see this many, many times. It's a great way of addressing into arrays, because array has a base address and you try to get an element in some offset or index. It could have been called base plus index. In fact, in x86, there is also base plus index. It's called base plus index, let's say. So let's take a look at load word in byte addressable MIPS. So we want to load a word into a register, 32 bits, but our ISA is byte addressable, right? So we're going to look at MIPS assembly. This is our high-level code, A2. MIPS assembly, if you so if these elements are in words, and we want to basically each element is 32 bits. You have A0 with 32 bits, A1, index 1, 32 bits, index 2, 32 bits. The address of index 2 is really at offset 8 because each element is 4 bytes, right? Meaning that the 0th element is at base address A. The first word, the first element is address A plus 4, and the second word is address A plus 8. That's why we need to multiply the index with the number of bytes in an element, okay? That's why this is 8 over here. Basically, if you really want to convert this high-level code that loads a word, which is a 32-bit element, in byte addressable MIPS, you basically need to translate it into this. What does this mean? This means that, assuming that the base address A is stored in S0, you add 8 to it, and that's the address of the word. And then you access memory with that address, and the data value is the element that you're looking for, okay? So why does, as I said, byte addresses are calculated as word address times bytes divided by word. Here you have the word address or the element address, right? Element size. Your element size is 4 bytes per word. So you need to multiply 2 by 4. If this was 1,000, you also multiply it by 4. So you will get 4,000 over here, assuming you fit in the offset. Okay. So you get 4 bytes per word in MIPS. If LC3 were byte addressable, you would basically use 2 bytes per word. So it will be a little bit different, but again, you don't need to worry about it right now. Okay, let's take a look at some other instruction format with immediate. So this is basically not other instruction format, but how this actually gets encoded, because we need to have an immediate value right now, which is the literal 8 value over here, right? So let's take a look at a similar example. This is the MIPS assembly we just showed. This is an LC3 assembly as a similar example actually to earlier. So basically, this is LDR. This is load word. Essentially, the same instruction in both machines. And this is what the encoding looks like in LC3. You have an opcode, you have a destination register, you have a base register, and the offset is encoded as a 6-bit value over here. In MIPS, it looks a little bit different. It's called an I-type instruction, immediate type. You have an opcode, the top 6 bits, as you can see over here, 35 happens to be that way. And then you have the base register, and then you have the destination register over here, and then you have the 16-bit immediate. Okay, so it really depends on the ISA how you encode it, but it's very similar, as you can see. There's not much different. And we're going to go into these formats a little bit more later on because we're actually going to build up an assembly programming tomorrow. We're not going to be able to finish the entire instruction sets today, but we're going to cover the instruction processing cycle. But we're going to go more into instructions tomorrow, essentially, and build up programs with it. Right now, hopefully this is very clear. You need to get an address, and the instructions need to encode the load instructions as well, right? The encoding needs to specify how you specify the load instructions as well. Okay, so now I've given you an overview of the instruction formats as well. Let's talk about the instruction processing cycle, because we're going to see more instructions and how instructions are processed. Without knowing the instruction cycle or instruction processing cycle, it's very hard to really understand how instructions are really processed. So we're going to go a little bit into microarchitecture right now based on the architecture specification. Okay, but essentially, how are these instructions executed? I'm giving you some instructions. How do we execute them? So basically, by using the instructions, we can speak the language of the computer, meaning we know how to tell the computer to execute computation in the ALU by using, for example, an addition. We know how to access operands from memory by using the load word instruction. But how are these instructions executed on the computer? Essentially, the computer follows a very rigid and simple principle. It has an instruction cycle and it keeps repeating it. It's called an instruction cycle or instruction processing cycle, not to be confused with a clock cycle. An instruction processing cycle may take multiple clock cycles or a single clock cycle. It has nothing to do with the clock cycle. This is really how the machine executes an instruction. This just happens to be called a cycle, unfortunately. Okay, instruction processing cycle is a sequence of steps or phases that an instruction goes through to be completely executed or processed. And these are the 6 steps that are general enough to execute any instruction. You need to fetch the instruction, decode it, evaluate its address, fetch its operands, execute it, and the store results. Okay, we're going to see this. Not all instructions require the 6 phases. The more sophisticated instructions require all. All instructions require fetch and decode. That's for sure. But not all instructions require every phase. For example, load register, like load word we saw earlier, does not require execute, right? Because it doesn't do any execution in the at least addition to store the result somewhere, right? It requires some execution to evaluate the address, but we already have a separate phase for it, right? Evaluate address. So it doesn't need to execute in the ALU. Add doesn't need to evaluate address, because add in the ISAs that we're examining operates on registers or immediates, and there's no reason to evaluate the address of a memory location because it doesn't require something from memory. Okay, so hopefully this is going to be even more clear as we go through different instructions. So Intel x86 instruction, for example, it has a different add. You don't need to know exactly what this is, but this means that take a value in a register and then get a value from a memory location, add them, and to store the result in the memory location. It's an example of an instruction with all 6 phases. It evaluates the address for the memory, and then it also needs to do the execution and then write back the result to memory. Okay, but we don't have such instructions in MIPS or LC3. That's why these are simpler ISAs that are better for instruction, easier for instruction to begin with. But in real world, the ISAs may be more complicated, as you can see. Okay, so every instruction goes through this processing cycle, and after the store result, you go back to the fetch of the next instruction. That's why this is called a cycle. You keep repeating it, basically. Okay, and then again, this has nothing to do with the clock cycle. A processing of an instruction may take 1 clock cycle or hundreds of clock cycles, as we will see later on. It doesn't matter. You fetch the next instruction after you finish the previous instruction, however many cycles each instruction takes. Okay, now let's take a look at these phases, and then we're going to finish up today. So the fetch phase obtains the instruction from memory and loads it into the instruction register. This phase is common to every instruction type. You have to fetch an instruction to be able to execute, right? So the complete description of it is as follows. First, you need to load the memory address register with the contents of the program counter, as I said earlier, actually. And simultaneously, you need to increment the PC so that you actually get the program counter or the next instruction. Again, this is a choice. You don't necessarily need to increment the PC at this point. You just need to increment the PC before you fetch the next instruction. Okay, and then the second step is to interrogate the memory. This results in the instruction being placed in the MDR by memory, as we discussed, memory data register. You may need to wait for some time, of course. You need to. And then the next step is to take the data that's inside the memory data register and place it into the instruction register, because now the memory data register has the contents of the memory location pointed to by the program counter. Let's take a look at how this happens in LC3 microarchitecture. Okay, basically the first step is load the MAR and increment the PC. So what do? We take the program counter, gated onto the bus, which means that we need to enable this control signal so that the program counter value gets gated onto the bus and it travels, and gets, at the end of the clock cycle, gets latched to the memory address register. And you need to enable the load memory address register signal so that that happens. So that's the first step. And then also concurrently, at the same time, PC gets incremented by 1. So you need to enable load PC. So while the old PC gets latched to the memory address register, new PC value, PC plus 1, gets latched to the PC. That's the beauty of concurrency in hardware, right? Now you latch the old PC, you're going to access memory with it, but the new PC value is something else. Okay, that's step 1. Step 2, memory address register, which contains the contents of the old program counter, which is the instruction we want to fetch. Essentially, you enable memory to access to do a read access. There are some control signals over here that you need to enable, and the memory gets accessed, and the data at some point gets put into the memory data register by memory. And then the next step is really to take the data that's put onto memory data register, gate it into the bus using the gate MDR signal in the next cycle. And then the data gets to the instruction register, which means that you need to load the instruction register, enable the instruction register, right? So hopefully this is very clear, right? You have 3 steps, and we have the data path and control signals to execute a fetch operation. Okay, so decode phase identifies the instruction. As I also said earlier, it also generates a set of signals, control signals, to process the identified instruction in later phases of the instruction cycle. Recall the decoder from lecture 5. I'm not going to show you again, but we had a 4 to 16 decoder, and it identifies which of the 16 opcodes is going to be processed. The input is the 4 bits, instruction register, top 4 values of the instruction register, because we have the instruction in the instruction register. The input is those four bits at the top. And the remaining 12 bits identify what else is needed to process the instruction, meaning the operands, as we discussed, right? So decode is very simple. If you look at this machine, it identifies the instruction to be processed. The instruction is already in the instruction register. You basically have the wires connecting it into this logic, this blob of logic, which generates the control signals. So it basically generates the control signals to process the instruction in the later phases of the instruction processing cycles, including the control signal for the ALU, including the control signal for the multiplexers, etc., including the source register 2, source register 1, destination register signals, etc., depending on what the instruction is supposed to do, as we will see later on in more detail. Okay, the next phase is evaluate address. This phase computes the address of the memory location that is needed to process the instruction, as we have seen. This phase is necessary in LDR, load register, load word, for example. It computes the address of the data word that is to be read from memory, as we have seen earlier, right? As we have seen earlier, there's a base plus offset addressing mode. We add the offset to the content of a register. But this phase is not necessary in add, so add doesn't do evaluate address, for example. Let's take a look at how it happens in LC3. Basically, the load register, if you have an opcode that specifies load register, you need to calculate its address by adding a register, source register 1, to an immediate. This is how it works. So for purposes that we will discuss later on, we don't do it through the ALU. We do it through a special adder. That's called an address generation adder. That's not shown here, but we will see later on. But basically, you take the value in source register 1. Source register 1 is specified in the instruction register for the LDR. And then you add to it an offset specified inside the instruction, if you remember. Base register plus an offset. And then the value is really the memory, it goes into the memory address register, right? Okay, but we'll talk about that in the next stage. This is how we evaluate the address of an operation. Base register plus offset. And both of those values are specified in the instruction register as signals to process the instruction. Okay, the fetch operands phase obtains the first operands needed to process the instruction. In LDR, we need to load the memory address register with the address value calculated in the previous evaluate address phase. Then read memory, placing source operand in MDR. And then in add, we obtain the source operands from the register file. So let's take a look at that. But in some microprocessors, operand fetch from register file actually can be done at the same time the instruction is being decoded. So you can actually play tricks to maximize your performance. You don't have to do it exactly in this phase if you can do it earlier, right? Okay, let's take a look at how it's done in LDR. So LDR, you may remember, we calculated the address over here with a different address. We load it into the processor bus, and it basically goes into MAR. And then we access memory just like we did earlier when we fetched an instruction. Now the MAR contains the base plus offset that gets loaded into the MAR. And then the data value from memory at that location is placed into MDR. And then you get the value and place it into the register file, as we will see in a little bit. Okay, execute phase executes the instruction. In add, it performs the addition of the ALU. In XOR, it performs the bitwise XOR and ALU. So it really depends on, this is really easy as we have discussed. So for example, for add, you may add SR1 and SR2, and the result becomes available at the end of the ALU, as you can see over here. Okay, that's very simple. Now the store result phase, which is the last phase, it writes the result to the designated destination. Once store result is completed, a new instruction cycle starts, or instruction processing cycle starts with the fetch phase. Now let's take a look. Store result. So add, for example, loads the ALU result into DR. So ALU result was here. We gate it onto the bus and then place it into the register file. And we know what the destination register is because it's in the instruction register, right? So we orchestrate the control signal such that this happens in the store result phase at the right clock cycle. Makes sense, hopefully, right? So basically processing happens in multiple clock cycles, and you basically orchestrate the control signals so that the right thing happens at the right clock cycle. And you can orchestrate the clock signals because you know what instruction is being processed in the instruction register, right? Okay, so LDR, load register, remember the data value was in the MDR. It gets placed into the destination register because LDR is a different instruction, right? Okay. Okay, so basically now I'll give you an example of the instruction cycle, all the way from fetch, decode, evaluate address, fetch operands, execute, and store result. And you keep repeating this essentially forever in a computer. So we will very briefly talk about changing the sequence of execution also before we conclude. A computer program executes in sequence, right? In program order. First instruction, second instruction, third instruction, and so on, unless you change the sequence of execution. So control instructions allow a program to execute out of sequence. They can change the PC, program counter, by loading it during the execute phase. So this is really important. You load it during the execute phase. And that wipes out the incremented PC that was loaded during the fetch phase. So an example instruction that changes the sequence of control is unconditional branch or jump. It unconditionally changes the control flow. And basically in LC3, it looks like this. This basically says jump to the address, change the PC to the address that's inside register 2. And it looks like this. This is the opcode, and this is the base register, and all of the other bits are encoded as zeros. Okay. So a base register is that. And essentially, PC gets the value inside the register identified by the base register. So simple. This is register addressing mode. This addressing mode has a name. It's not register plus offset. You just use the value in the register as your address that gets into the PC. So there are variations of this. A return instruction, for example, is a special case of jump, where base register is R7 in LC3. And there are other ISAs that have different Rs, register numbers for return. And jump to subroutine are other instructions that enable you to jump and store the program counter of where you're jumping from, for example, as we will see. So jump in MIPS is actually very similar, but except it doesn't use a register. So this is called an unconditional branch or jump, but the target is encoded in the instruction itself. So this is the opcode, 6 bits, and opcode is 2. And target is encoded as this 26 bits. And this is called a J-type instruction. So 2 is the opcode. Target address is computed as this way, basically. You take the top 4 bits of the incremented program counter and concatenate it with the target sign extended and shifted by 2. Multiplied by 4 means shifted by 2, right? So this gives you a 28-bit value. And essentially, you have a 28-bit value concatenated with a 4-bit value. So you have a 32-bit value in PC, right? So basically, this is called a pseudo-direct addressing mode. Don't worry about it right now. I'm not going to test you on what is the name of this addressing mode, but it's a pseudo-direct in the sense that you basically take the address and directly calculate it from the instruction bits, right? The address is encoded in the instruction bits plus the program counter, right? But it's also, it's not, you don't do an addition, basically. You do a concatenation. That's kind of very direct. So there are variations of it. Jump and link, for example, that enables function calls, jump register. So this is the equivalent of the jump that I showed you earlier. So this is jump register in LC3, and this is jump register in MIPS. Basically, you set the program counter to the value in register as 0 in this case. It uses the register addressing mode that we showed earlier. So basically, LC3 data path we have seen earlier, gate PC, LDMAR, multiplexer, etc. At this point, I think this is maybe I will very quickly cover the jump instruction cycle, and then we're going to finish. But basically, where does the jump go into? Basically, you can see that ignore the gate PC over here. I'm going to show you the jump before I show you other stuff. But basically, jump instruction gets executed by taking the register, one of the registers, source register 1, and placing it into the program counter. So you can see the path for it, right? Source register 1 out gets selected to be loaded into the program counter in the execute stage of the jump instruction. So clearly, there's a path over here to enable the loading of a register into the program counter. And you can see the different kinds of jumps in the opcodes in LC3. Jump is here, jump to subroutine is here, and jump to subroutine by saving the register is over here, register mode over here. So there are different addressing modes also in LC3, which we will cover in the next lecture. But if you're interested in how we actually control the instruction cycle, this is a state machine-based representation of it. So this is the fetch part. As you can see, basically, I've shown you all of the fetch parts earlier. PC gets loaded into MAR, PC gets incremented in state 1. In state 2, in the next clock cycle, the MAR, the memory responds with the data in the address that's in MAR and placed into the MDR. And then in state 3, MDR gets loaded into the instruction register. So that's the fetch phase, if you will, in the finite state machine. So there's a finite state machine that controls all of this. And we will see this in more detail. I just want to finish up with this one so that it can jog your thinking a little bit. And then you decode the instruction in state 4. The finite state machine goes to the next state, depending on the opcode, as you can see over here. Your next state really depends on the opcode. If it's add, you basically do the addition. If it's load, you do whatever is needed for the load. If it's jump, basically you execute the jump. Let's take a look at how a jump is executed. Basically, in some state, jump loads the register into the PC. So there, as I showed you in the data path, there's a path from the register file into the PC, and that's what's happening over here. And each state, you assert the right control signals. Basically, here you assert the right control signal so that PC goes into MAR and PC gets incremented. And here you assert the right control signals to do this. Here you assert the right control signals to do this. So basically, it's a beautiful way of really controlling the transition between the states and what each state is supposed to do. And we're going to cover this in full in the next week, essentially. Not really tomorrow, actually, but in the next week. But if you want to get ahead and take a look, you can see the full state diagram in Pat and Patel Appendix C. Clearly, this doesn't show you the full state diagram. Okay, so that's the end of the instruction cycle, and that's a very good place to finish. Now that we've covered all of this, we will cover more of LC3 and MIPS instruction set architectures tomorrow, and we will also cover assembly programming since it's very tightly integrated with instruction set architectures. And then next week, we will start with microarchitecture. Any burning questions? Okay, I see a bunch of questions answered by people. That's good. So I think feel free to ask questions on different forums where we have questions. So you can maximize your thinking, if you will. I will see you tomorrow. Take care.